We now know that the four fundamental subspaces of a matrix pair off into orthogonal complements of one another. Let's see how this can be used to solve problems. So here I have an example of a 3x4 matrix, and I've written down, or I've drawn the picture of the four fundamental subspaces of this matrix. I went ahead and I found a basis of the column space. That basis consists of the vectors 1, 1, 5 and 4, 3, 24. And I also found a basis of the left null space. And here I only had one basis vector, and that basis vector was -9, 4, 1. Okay, so I have a basis of the column space, and I have a basis of the left null space. Before we say anything about this new perspective of orthogonality, let's remind ourselves what we can say about dimension. Well, I have one basis vector for the left null space, which tells me that the dimension of that space is 1. And I also know that I have a basis of the column space, and the number of vectors is 2, so the dimension of the column space is 2. Of course, this makes sense because the sum of those two dimensions must be the number of rows of my matrix, which is 3, so that's fine. Once I know that the dimension of the column space is 2, I immediately know that the dimension of the row space is 2, because the dimension of the column space is always equal to the dimension of the row space, and that number is the rank of the matrix. And finally, once I know that the dimension of the row space is 2, I can figure out the dimension of the null space, because the dimension of the null space plus the dimension of the row space must equal 4. And so in this case, the dimension of the null space, which is the nullity of this matrix, must be 2. So that's a little refresher on dimension. The question now is, well, how do knowing that these little orthogonal signs added into the figure actually helps me with any sort of problem? Well, let's think about the problem of testing whether or not the vector 3, 5, 1 is in the column space. So how might we solve this problem traditionally? Well, one thing we could do is what I'm calling an inefficient method. We could check whether or not 3, 5, 1 is a linear combination of our basis vectors of the column space by putting the basis vectors for the column space into the columns of the matrix, and then augmenting with 3, 5, 1 and checking for consistency. We did that here, and what we're finding is that the resulting system is inconsistent. So this tells me that the vector 3, 5, 1 is not in the column space. Now, why am I calling this method inefficient? I'm calling this method inefficient because it involves row reductions, and I want to try to avoid row reductions whenever possible. So this is the Hegelian principle, I guess. If I'm going to call something inefficient, I should probably tell you something that's I consider to be efficient. So let's ask ourselves, well, what does it mean to say that a vector is in the column space of a matrix? Our new perspective on the four fundamental subspaces says, well, being in the column space is equivalent to saying that vector is orthogonal to every vector in the left null space. So if 3, 5, 1 were in the column space, we would certainly expect it to be orthogonal to the vector -9, 4, 1. Well, checking that orthogonality condition is exactly what I consider to be the efficient solution to this problem. If we take the vector 3, 5, 1 and then take an inner product with our basis vector of the left null space, we get -6, which is certainly not equal to 0. This immediately tells me that my vector is not in the column space of the matrix, and I haven't had to do a single row reduction. So I sort of cheated here on the left because I outsourced the calculation to a computer, whereas the calculation on the right here is not so bad. It's just a little bit of mental arithmetic to figure out this inner product is -6. So this is sort of like our perspective on things, is we'd like to always, we always prefer efficient methods over inefficient methods. And this perspective of orthogonality allows us to work more efficiently. Let's look at another problem. So here we're defining V to be the span of this list of 2 vectors. Well, so what does that mean? Well, one tangible way to wrap our heads around span is to represent this V as the column space of the matrix obtained by inserting these two vectors into the columns of a matrix. Now, when I put these two vectors into the columns of a matrix, the matrix ends up being 4 by 2, and I have my picture of the 4 fundamental subspaces. The space I'm interested in is the column space of this matrix. And one thing to note here is that the two columns of this matrix are certainly independent because they're not multiples of each other. So I know those two columns give me a basis of this space. Well, keep in mind that we understand the 4 fundamental subspaces really well. In previous lectures, we discussed how to explicitly construct bases of each of the 4 fundamental subspaces. So once I can interpret the V I'm interested in as one of the 4 fundamental subspaces of a matrix, I can now apply all of my numerical methods to study this vector space V. So one thing I can say is that V has dimension 2 because I have 2 basis vectors here. And once I know one of the dimensions, I know all of them. The dimension of the left null space, which is the orthogonal complement of the column space, must be 2 because these two dimensions must sum to the number of rows, which is 4. The dimension of the column space is the rank of the matrix, which is also the dimension of the row space, so that dimension is 2. And the dimension of the row space plus the dimension of the null space must equal the number of columns, which is 2, which tells me that the dimension of the null space is 0. Now, let's say that somebody asks us to find a basis of the orthogonal complement of V here. Well, we shouldn't be intimidated because we know that V is the column space of this matrix, and its orthogonal complement is the left null space of this matrix. And we know how to numerically find a basis of the left null space. We transpose the matrix and solve the system A transpose X equals the 0 vector. I went ahead and did that, and I found 2 basis vectors, 3, 1, 0, 0, and 1, 0, negative 2, 1. Of course, we can verify that these 2 vectors make sense by checking that both of them have inner products with the 2 basis vectors of V here that equals 0. So the punchline here is that if somebody defines V abstractly in this way, we can convert this abstract definition into something numerical that's much easier to work with. So never be intimidated by span. Just convert the span definition into the column space of a matrix and then work numerically. And the last thing I want to mention here is that this perspective of orthogonality is related to one of the factorizations that we've studied previously. So we've actually seen this identical slide before. This is a fact about EA equals R factorizations. If our matrix A is M by N with rank R, so like this example here, this is an EA equals R factorization, so I can figure out the rank of A by looking at the number of pivots in R, of which there are 2. So A here is a 4 by 3 matrix with rank R equals 2. And remember, when we studied EA equals R factorizations, one thing we noticed is that it will always be the case that the last M minus R rows of E are orthogonal to every column of A. So we see that explicitly in this example. If I take an inner product of the 3rd row of E with all 3 of the columns of A, I'll always get 0. If I take an inner product of the last row of E with all 3 columns of A, I'll always get 0. So the bottom M minus R rows of E in EA equals R are all orthogonal to the columns of A. Well, what's our new perspective on the 4 fundamental subspaces? Everything orthogonal to the columns of A must live in the orthogonal complement of the column space of A, which is the left null space of A. So what this is saying is that those last M minus R rows of E give us a basis of the left null space. So we can state this as a theorem. Let's say we're studying EA equals R, where A is an m by n matrix, and the rank is equal to little r. So here we have that example again. The punchline of this theorem says that the last m minus r rows of E always form a basis of the left null space. So if somebody gives me this EA equals R factorization, there are many things I can do with it, but now I have an extra thing I can do with it. So here, this is a 4 by 3 matrix with rank 2. So m is 4, r is 2, so m minus r is 2. So what this is saying is that the last 2 rows of E here form a basis of the left null space. So here I know that the left null space is the span of those last 2 rows of E. This automatically gives me a basis of the left null space. And so now, if I wanted to test whether or not a vector is in the column space, for example, I don't need to do any row reductions. All I need to do is take an inner product of that vector that may or may not live in the column space with these 2 basis vectors of the left null space and check whether or not I get 0. So we have a new toy to play with, the orthogonality of the 4 fundamental subspaces, which is represented in the figure. So we'll see more and more that this perspective pays dividends down the road.